I want to give a quick overview of what statistical distributions are so we can better understand why they're so important for hypothesis testing. Let's start with the definition of probability, and it's pretty simple. It's just the chance of a given event happening. And it's a number from 0 to 100% or from 0 to 1, depending on the unit of measurement you're using. And for any single event, we can calculate a probability. So, for example, the chance of flipping a coin and it being heads or tails is going to be 50%, or 1 divided by 2. A probability distribution describes the probability for all possible outcomes of a given scenario. And one important property of a probability distribution is that we can calculate the expected value. We also call that the average. This is a 20-sided die, and this, what you're seeing here, is a probability distribution for that 20-sided die. There's 20 possible outcomes in total, a number from 1 to 20, and each number has a 5% chance of being rolled, 1 divided by 20. Now, this is what we call a discrete probability distribution, meaning that we don't have a continuous, you can't roll, for example, a 1.5 or a 17.78. We can only roll discrete or integers. So there's not a probability for rolling a number between 1 and 2. You're either rolling 1 and 2, and so on. Now, the way we calculate probability for discrete distributions, and this is actually true for continuous distributions as well, which we're going to get to in a second, is what we call area under the curve. So we can calculate the probability, for example, of rolling greater than 17. And for the nerds out there, 17 is the armor class of hobgoblin enemies in the game Dungeons & Dragons, where you often see 20-sided dice being used. So what is the probability of our hero adventurers rolling greater than 17 and hitting the hobgoblin enemy? The first way is taking advantage of this discrete probability distribution by just adding up the probabilities for rolling a 17, 18, 19, or 20. And because we know that's 5% each, we add that up, and that equals 20%. We can also calculate the probability of rolling 17 or greater just using the equation that was in the last slide, which is the probability or the number of ways that this event can happen. There's 4 possible ways you can roll 17, 18, 19, or 20, and there's 20 total possible outcomes. So we land to the same answer, 20% either way. What you see here is a sampling distribution when I rolled the 20-sided dice 4 times and counted the number of times I rolled each number. This looks a lot different than the theoretical or population distribution I just showed you earlier. If I rolled 40 times based on that population distribution, I should have rolled each number twice, right? Because I have 40 rolls, 5% chance of each number, and you do the math, I should have rolled each number twice, exactly 2 times. But that's not what happened. When you look at the sampling distribution, I rolled 9, 15, 17, 20, 4 times, so twice as much as expected. Okay, and when we look at the sample mean, it's 12.5 versus the theoretical mean of this population distribution, which is 10.5. So I'm actually kind of overestimating my mean. So assuming I had no understanding of the underlying or theoretical or population distribution, I would say, okay, the average is 12.5. If you roll a 20-sided die, the average value you get is 12.5. And that's with 40 dice rolls. When I roll it 200 times, well, it still doesn't look exactly like the population distribution. In theory, I should have rolled each number 10 times in 200 dice rolls. But you can see that the mean, the average value, the average 20-sided dice roll is 10.4. And that's very close to the population mean of 10.5. So this is the law of large numbers in practice. In contrast to discrete variables, continuous variables can take an infinite number of values. For example, unlike rolling a 20-sided die, you can't roll 17.78. You can have a cow that produces 17.78 liters of milk or 17.7893218 liters of milk. Similarly with things like measuring yield or percent weed control. These are continuous variables. Even if the precision of our instrumentation doesn't allow it, we have to understand that these are continuous variables. For example, let's say you're evaluating, the percentage weed control from 0 to 100. Chances are you're going to give a whole number. You're not going to rate a plot as having 48.7982% weed control. Just visually, you're not going to go down to those, decimal places. But it is a continuous variable still, because it is possible for a plot to have 17.5% weed control. So even if the instrumentation doesn't allow us, most variables that we do measure can be divided into an infinite number of variables. So here's a continuous probability distribution you probably experience every day if you take the bus to campus, which is just waiting for a bus at a bus stop. Let's say the bus is scheduled to arrive every 15 minutes. So you show up at the bus stop, and there's a probability that you have to wait 15 minutes if the bus just left, or 0 minutes if the bus is just pulling up as you get to the bus stop. And also, because we're in a continuous probability distribution, you also have a chance of waiting between 0 and 15 minutes. Okay, so this is a continuous probability distribution. Notice there's no gaps because you can wait 7.823192 minutes for the bus, as opposed to our discrete probability distribution where you can either roll a 7 or an 8. Okay, so how do we calculate probabilities with continuous distribution? So unlike discrete probability distributions where we just added things up. We just added the probability of rolling 17, 18, 19, and 20 together. In a continuous distribution, we have an infinite number of values, and we'd have to, essentially add up an infinite number of numbers to get the probability, and we can't do that. That's impossible. So what we do is always look to the area under the curve. We look at the area under the curve, and that's how we calculate our probability for a given event occurring. So what's the probability of waiting for 10 minutes or longer at the bus stop? Basically, we have this rectangle, and we just calculate the area of this rectangle, basically the whole distribution to the right of 10 minutes, so waiting 10 minutes or longer. And we know the x-axis, we know the long side of that of that rectangle is going to be equal to 5 because we have 5 minutes between 10 and 15 minutes. And on the y-axis, we have our probabilities, which is 6.67%. Basically, this is what we call a uniform distribution because the probability of waiting any amount of time, 1 minute, 10 minutes, 10.5 minutes, is always equal to 6.67%. We multiply that together. The area under the curve is 33.35%. And that's our probability of waiting for 10 minutes or longer. Now, there's many other types of continuous distributions aside from the uniform distributions that I've been showing you. This is a bimodal continuous distribution. This is something that would happen if you were, say, working at Uber Eats or DoorDash and you were analyzing the probability of the average order value that a customer has. What's the chance of, say, a customer ordering a meal delivered for, worth $10 or $20 or $25, whatever. And you get this bimodal distribution when you start offering discounts. So let's say I was DoorDash and I said, hey, if you order $25 minimum, you get free delivery. Then, you're going to have lots of people making small orders like 15. But if you have someone that has $25 order, they're going to be like, well, if it's $5 delivery, I might as well just put in a $25 order of food and then get free delivery. So, we see this bimodal distribution where we just basically have very few people ordering $20 meals and a lot more people ordering either smaller, like $15 or $25 meals. We also have, and this is probably the most important distribution, we call this the normal distribution. This is going to be very important for hypothesis testing because of what we call the central limit theorem, which is going to be covered in the next lecture. But this is going to be kind of our guiding star, our North Star, the normal distribution. It's going to be very important for us in the rest of the course. So in summary, what do I want you to take away? You have to be able to define what a probability distribution is and how to calculate the chance of discrete probability events occurring. You have to be able to, figure out if a variable is discrete or continuous. So that might be a quiz question. Figure out, is this variable discrete or continuous? And you have to be able to basically remember what the law of large numbers is. Okay.